And so let me tell you about what I'm going to talk about today. I thought it would be fun to just reflect on the concept of spin, which was discovered just under 98 years ago and was very controversial. But I'm going to tell you about how it connects to what I'm interested in, which is really the spin as a source of Hilbert space for new forms of entanglement in quantum matter. The people who work with me on this, primarily on this project, are my old friend and colleague Alexei Svelik at Brookhaven National Laboratories, and 3 young people at Rutgers, Aditya Panigrahi, Zekun Zhuang, and Tamagna Hazra. Tamagna, in fact, is going to be moving to the KIT next year, so he's going to be in the vicinity. I hope you'll make his acquaintance soon. And also, the work connects with older work with Yasha Komijani, Premi Chandra, my colleague at Rutgers, Ona Ayrton, Ho Yao Chang, and Ari Wugalter, who has now become a lawyer. So the pictures there tell you something about what I'm going to tell you today, and it'll keep you guessing, including the TARDIS, which you will see there's a second element. If you don't know what a TARDIS is, I'll tell you later. And that's what I'm going to talk about. A century of spin. Going to tell you about the motivation that stimulates some of my work, strange insulators and superconductors. I'm going to talk about fractionalization and the view that I hold that it's a kind of emergent second quantization. And I'm going to tell you about work we've been doing on the CPT model. It's a new form of Condor lattice that combines a kind of Kitaev or Yao Li model with the Condor lattice and tells us about a new kind of pairing that can come about. Okay, so let's get going. We started at 3 minutes past. It's now 4 minutes past. Okay, so this is Ralph Kronig. He's a German he was a German who was born in Dresden, but he was one of the first young fellows to go across to North America and pursue a career there. He was a graduate student at Columbia, and he met Paul Ehrenfest, who encouraged him to go to Europe and learn about the new quantum mechanics. He went to a talk by Wolfgang Pauli, and this gave him the idea there should be another quantum number, which we now call spin. Unfortunately for him, Heisenberg and Pauli hated the idea. This is the words from Pais, Abraham Pais. And in fact, Pauli came to Kronig and said, it's a very clever idea, but of course it has nothing to do with reality. And this poor graduate student, intimidated by this great figure in physics who went on to become famous because of spin, never submitted his idea for publication. Let that be a warning to you all, okay? By contrast, there were 2 other young graduate students, and here's a picture of them here, with Kramers in the middle, but really it's Uhlenbeck and Samuel Goudsmid. These were students of Paul Ehrenfest in Leiden. And in those days, maybe today too, when you had a new idea, you would write it up as a small note that would be published. It was the early version of what would be a phys-rev letter today. And so Uhlenbeck and Goudsmid had the idea of spin, and they wrote it up in a small note, and they gave it to their advisor, Paul Ehrenfest, who's not shown here. And it was actually published, or the date of discovery is dated the 17th of October, 1925. But just to check on the ideas, they went to talk to Heinrich Lorentz the day before. This is all documented. And Lorentz, being an expert, told Uhlenbeck that actually this idea of the spinning electron is completely incompatible with classical electrodynamics. And of course, that's true because you've got this charge that's whizzing around. It would radiate like crazy, right? And so Uhlenbeck became petrified, and he asked his advisor to withdraw the paper. Fortunately for him, however, the day before, or maybe a week before, Ehrenfest had sent it off for publication. So he admitted to his students that he'd already sent their paper to Nachenwissenschaft, which is where it was published. And he added that, well, you're both young enough to be able to afford a stupidity, okay? And so this was the reception that this new idea had in 1925. And some of those who thought it was hateful and horrible became famous for their work on it. Sadly, Uhlenbeck and Goudsmid were not awarded the Nobel Prize, but they received more or less every other prize, including the National Medal of Honor that was given to Uhlenbeck much later in his life by Jimmy Carter. So anyway, What about spin today, 100 years later? Well, of course, we think of it as the elementary qubit of the world we live in. It, of course, has been essential for magnetism and the evolution of our ideas on broken symmetry in antiferromagnetism. It is absolutely vital for the chemical bond. You couldn't have a chemical bond without two particles that could go into it. We know that, we heard this week, that spin fluctuations can provide the pairing glue for superfluidity and superconductivity. Perhaps the most famous case is the case of helium-3b, where the ferromagnetic fluctuations are thought to drive the A phase and the B phase. Of course, in our modern world, we relabel the spin by 1 and 0, and it is the basis for the modern world of quantum information. This is the famous Bell state, which enables us to understand that there are no hidden variables in the world because the correlation's built into it. But what I want to talk about today is really the spin as a provider of Hilbert space, real estate in the quantum mechanical sense. And this quantum mechanical real estate provides the basis for many new entangled states of matter. And I'm going to particularly talk about the interplay of Kondo lattices and spin liquids. Let me show you some data that will illustrate this. This is a not very well-known superconductor. It's a kind of 115 superconductor discovered by Dai Aoki. Its property is that in the normal state, it is a Curie paramagnet. You can see this beautiful, Curie-Weiss susceptibility here that goes all the way down to its 4 Kelvin transition temperature. And here is the specific heat. And it's got a huge anomaly there. And of course, we all know that in the modern sense that when you integrate up the specific heat divided by temperature, we get a measure of the entanglement entropy. In this case, you get about 1/3 R log 2. So half the entropy of this low-lying Kramers doublet, or 1/3 of it, goes into forming the superconducting condensate. Okay, so we can be sure that in this system, the spin entanglement drives the pairing. In fact, the order parameter contains the spin in some mysterious way. Okay, so let me use that as an entry to some of the systems that fascinate me at the moment, and these can be clarified as being strange insulators and strange superconductors. And why are they? Well, this is samarium hexaboride. It's a topological insulator, and it has this very nice plateau in its conductivity at low temperatures. It has an exponentially activated conductivity. You can extract a gap of about 3 millivolts. For a long time, we believed it was a conventional renormalized band insulator. Then we discovered it was probably a conventional renormalized topological band insulator. But it still has some surprises in it. And one of those surprises is the fact that it seems to exhibit quantum oscillations. You can measure these oscillations, not in the conductivity. There are no oscillations in the conductivity, mysteriously, even though it has conducting surfaces. But there are oscillations in the free energy, in the magnetization, and most recently, these oscillations have been measured from the specific heat capacity by Art Ramirez. And what's important about these oscillations is that they show that the fluctuations in the specific heat capacity are a large fraction of the residual specific heat. This system has a residual linear specific heat, and they show us that they can't come from a minority phase of, say, aluminium inclusions, and they tell us that the oscillations seem to be real. Nevertheless, there's still a great deal of controversy associated with this system. Could it be that these are oscillations being driven by a very large field comparable with the 3 milli-electron volt gap? Or could it be that, as the authors of the paper, the science paper, that there may be a neutral Fermi surface? And if so, how the heck can a Fermi surface, which is neutral, exhibit the features of cyclotron motion? Seems to be contradictory. And so this is a very nice system. And one of the reasons we're interested in it is that it's been joined by 2 other materials, most recently iron diantimony. And these systems also exhibit robust quantum oscillations and linear specific heat. So let's talk about it. From the perspective of a Kondo lattice, a Kondo insulator is a system in which singlets have formed via this Kondo interaction that's scaled to strong coupling. And another way of thinking about it is to treat this problem using a large N expansion in which we decouple the spin as a bilinear of Abrikosov pseudofermions. From the more modern perspective, we can kind of think of this as a fractionalization phenomenon. And how do we think of that? Well, the physical Hilbert space of the spin is just up and down. It's a two-dimensional Hilbert space. But at low energies, the spin breaks up into fermions and develops an emergent Fock space. And to allow the Fock space to grow, in some sense at low frequencies, there has to be a compensating U1 gauge field that takes care of the constraints. And this is our way of thinking about the Kondo lattice at the current time. And so, in fact, the Kondo insulator is, in fact, from this perspective, a rather remarkable example. It's a kind of example of Oshikawa's large Fermi surface principle, in the case that the Fermi surface has expanded to fill the entire Brougham zone and make an insulator. Right? But the presence of a neutral Fermi surface, if it's there at all, it motivates us to examine the possibility of new kinds of spin fractionalization. Could the spin fractionalize into Majorana fermions? This is another way of representing the spin that we've heard about in this conference. It's something that we've played with for quite a while, since the early 1990s. And what it does is it gives rise to a different picture of the Kondo insulator, because there are no, when you look at the F electrons or the spins, they've now broken up into 3 Majorana fermions rather than 2 Dirac fermions. 3 Majorana fermions is equivalent to, 3 Majorana fermions has the property that they can't hybridize with the 4 Majorana fermions that describe a conduction band. Spin up, spin down is equivalent to 2 ups and 2 down Majorana fermions. And so one gets left behind, and you get the bizarre situation that you get a gapless Majorana band. When we did this in the 90s, we didn't have any controlled models of this behavior. It was a completely uncontrolled mean field theory. And moreover, we realized not long afterwards that we'd broken global gauge invariance. And so it couldn't be an insulator after all. It must be a superconductor. So we rewrote our original proposal as a theory for superconductivity, and it doesn't fit anything that's ever been seen in heavy fermions. And so we left it until in 2015, Bhaskaran turfed up our paper and said, well, maybe this is a way of thinking about the new quantum oscillations. And that got us thinking about this. And we started thinking about maybe this system was not really a well-defined superconductor. In fact, was a kind of failed superconductor, and more on that in the process. Okay, here, let me look at the second motivation. This is uranium ditelluride. It is a strange superconductor. Why is it strange? Well, one of its wonderful features is it has a low temperature featherweight transition temperature, but in a magnetic field, it believes it's a heavyweight superconductor. And this is the reason that the discoverers of this called it a Lazarus superconductor, Lazarus from Hebrew mythology. What's interesting about this is not only the very high upper critical field, look at it, you can see there is a reentrant phase here for a certain orientation of the field, which actually extends all the way up to 60 Tesla, despite the transition temperature being around 2 Kelvin. Okay. But it also has other mysteries to it. Let me show you some of those. In particular, at least in the early measurements, it exhibits broken time reversal symmetry. This is the Kerr effect measurements. And if you cool this in the absence of a field, you find it spontaneously develops a Kerr rotation. Moreover, scanning tunneling spectroscopy measurements exhibit a kind of Doppler shifted STM signal on step edges on the surface. And these have been interpreted in terms of a chiral edge state. And both of these, if they're true, are evidence for broken time reversal symmetry. Okay. And if that were the case, this would then be a chiral topological superconductor. It would be well, if you look at the table here, you can see that at least in 2 dimensions, if you have charge conjugation symmetry and broken time reversal symmetry, you have the possibility of a topological superconductor. This system is quasi 2-dimensional, so maybe that's what it is. Okay. But there is a problem with this system because the evidence suggests that there's a one-step transition to the time reversal of breaking state. Okay. Here are the most recent data on the system. It's a very clean transition. These samples haven't been around very long, and first attempts to do the Kerr rotation at Los Alamos have not revealed a Kerr rotation, a null result. And so there is a speculation that maybe there isn't any broken time reversal after all, but the Kapitounik group has not yet repeated their experiments. And so we don't know whether this was a feature of the early materials or not. Nevertheless, it's still an intriguing point. And one of the reasons it's intriguing is that if you look at the symmetry aspects of this system, in order to have a single stage transition into a chiral topological triplet state, you have to have two-dimensional representations of the triplet pairing group. And if this system were tetragonal, there would be a good candidate there, the EU group. But in fact, this system is orthorhombic. And so orthorhombic only has one-dimensional representations for the triplet pairing. And so this evidence suggests if there's a one-step transition to the time reversal broken state, which is impossible on the basis of orthorhombic symmetry. So you have two choices, and the choice you make determines your character. Choice number one is, well, it's obvious, according to BCS theory, since you can't have a one-stage transition into a broken time reversal state in an orthorhombic crystal, then it must be that the experimentalists got it wrong, or that the early samples are bad, and that this is a kind of fake property, okay? But if you've got the more radical point of view and say, no, hell, I think actually that more likely that when this is checked out, there will be a broken time reversal symmetry. And if that's the case, then it motivates a consideration of alternative classes of order parameter, classes that lie outside the BCS classification, okay? And that's the reason I showed you at the beginning of the Kronig story, because it's crazy, but it's interesting. So let's examine it, okay? Okay. And so I want to talk about fractalization, because I think it's a very important aspect of entanglement. And fractalization reminds us a little bit of second quantization. What is second quantization? It's the remarkable thing that although we use a Schrödinger equation to describe the behavior of particles, the natural way to describe their emergent behavior is to introduce a Fock space and to factorize every physical operator into particle creation and annihilation operators, okay? Now, of course, the time evolution of the state lies on a sheet of definite particle number. Nevertheless, we happily use creation and annihilation operators. We describe our Feynman diagrams. We think of a charge fluctuation as producing a particle pair. And all of this is controlled because the confinement of the physics to a slice of Fock space is controlled by a gauge symmetry that guarantees that at each point in space, the total number of particles is conserved, okay? So now let's look at fractalization. Fractalization is something that's been discovered perhaps since the early days of polyacetylene, or perhaps one-dimensional properties of spin chains. Here is the classic example of the Heisenberg spin chain, where when you attempt to create a magnon, a spin-1 excitation, it breaks up into two spin-a-half objects we call spin-ons. Here's the other classic example, the fractional quantum Hall effect, where the addition of an electron into a 1/3 state, it breaks up into 3 anions. And so in each of these cases, you have an emergent Hilbert space. The physical Hilbert space is confined to a slice, okay? But you get fractionalized excitations, and to describe them requires a Fock space that is larger than the physical Hilbert space. And so, for example, in the Kitaev honeycomb lattice, the magnons fractionalize into a quartet of Majoranas. One of those Majoranas is gapless. When you flip a spin, you create one of those gapless Majoranas plus a gap-full Vison. So the Kitaev spin liquid is actually a gapped spin liquid, but it's completely solvable. We can get right inside it. And we know that the description of the low energy physics is described in terms of an emergent Fock space, a space of excitations that is larger than the original Hilbert space, controlled by the fact that we have an emergent gauge symmetry. In this case, is a discrete Z2 gauge symmetry. So just to give you a kind of physical takeaway picture, what we really have in these situations is we have a physical Hilbert space, but to describe the excitations, we need to expand the Hilbert space into a larger Hilbert space, which is an emergent feature of the physics. And the description of that requires that there is indeed an emergent gauge field. For the case of the Kondo effect, for example, you need an emergent U1 gauge field. Okay, so this is where the picture of the TARDIS comes in. In Britain, this is a children's or adults science fiction program that's been going for about 60 years, and it involves time travel. And this is an old-fashioned police box that used to be in Britain in the 1960s or 50s. And the important thing about it is that the inside is bigger than the outside. If you go inside with Doctor Who, you can see the inside and it's bigger than the exterior, okay? We don't know how to make time machines, but we certainly understand that fractalization involves the emergence of Hilbert spaces that are larger than the state we started with, the Hilbert space we started with, okay? Okay, so moving right along, let me now take you to a solvable model of order fractalization. And this is the model we call CPT model. It's a model that combines a technology that is grown out of the Kitaev model. And the Hamiltonian for this contains three parts: electrons running around on this mysterious hyperoctagonal lattice, a spin liquid on the same lattice, and a Kondo interaction that links them together, okay? And so this is the electrons running around the lattice. And so the key part of this that makes it work is the discovery of a new class of gapless spin liquids, which go under the category of the Yao Li model. And I'm going to tell you about the Yao Li model, okay? In the Yao Li model, there are spin and kind of other orbital degrees of freedom. So it has a quartet of states at each site. And those orbital degrees of freedom behave as kind of ancillary qubits. They stabilize the low energy physics, but they gap out and they disappear. And what happens in the low energy physics is that the spins fractionalize in terms of Majorana fermions, in this case as vector or spin 1 Majorana fermions. So if you flip a spin, you create a pair of fermions. Each fermion has spin 1. Okay, that's what happens on this lattice. Okay, and then we Kondo couple that. This is the Yao Li model that I'll come back to in a moment. Okay, we then Kondo couple that with an exchange coupling to the local moments. If we didn't have the Yao Li part, then presumably these spins would fractionalize as heavy fermions. But because we've got the Yao Li spin liquid there, something different happens. Okay, and what happens is that the coupling to the conduction C leads to a Cooper instability at infinitesimal coupling into a superconducting state with a Majorana Fermi surface. And since the instability occurs at infinitesimal coupling, we can do a controllable treatment of this problem at weak coupling and prove that everything takes place. This is the phase diagram. So I'm now going to climb inside this model a little bit with you for about 5 or 10 minutes, first looking at the Yao Li spin liquid, and then looking at its coupling to the electrons. Okay, but this is the summary. Okay, so let's move ahead. Let's look at the Yao Li model. Yao Li model was discovered by Yao and Li in 2011, and it was in their case it was done on a honeycomb lattice, and we are going to generalize it using the discovery of Hermans and Trebst, who generalized the Kitaev model to higher dimensions. And this funny lattice here is key to their discovery. It's actually a BCC lattice, where at each point on the BCC lattice, you have a spiral of 4 atoms. That's what this is. And there are cross links between the spirals that make this into a system that's got chirality, but has actually got complete 3-dimensional cubic symmetry. Okay. And because there are only 3 connections to each site, we can use the technology of the Kitaev model. But in this model, in the Yao Li model, there is both a spin and an ancillary orbital degree at each site. That's to say, you've got spin 1/2 and orbital 1/2. So that's 2 times 2, 4 states per site, a quartet, okay? And they're coupled in this funny way in which you've got the conventional kind of Kitaev coupling between the orbital degrees of freedom, but decorated by an S.S, Si.Sj. This is the Yao Li model, and this is what we're going to look at in 3 dimensions on this hyperoctagonal lattice. We're really combining the observations of Yao and Li with the observations of Hermans and Trebst. Okay, so what happens in this? Well, there's the orbital and the spin degrees of freedom, and what happens is that the orbital degrees of freedom gap out, giving rise to a Majorana fractionalized spin liquid. So that's the classic picture that we all use. The orbital degrees of freedom form valence bonds, and they're gapped out on each side. But then what happens peculiarly is they liberate a single Majorana degree of freedom, A0. This Majorana in the conventional Kitaev lattice is the gaseous excitation. But in this case, it combines with the spins and converts them, fuses with them to create these Majorana fermions. And so that's the model we're left with. And let me tell you a little bit more about it. At low temperatures, the gapless degrees of freedom fuse gapped degrees of freedom, form Z2 bonds. It forms a gauge theory. This is the model that we now look at. And the only thing that's different to a conventional Kitaev model is that we have a triplet of Majoranas rather than a single Majorana hopping from site to site. Okay. So, and you can see here the Z2 gauge field, which is static, which commutes with the Hamiltonian. That's what makes it so solvable. Okay. So a lot is known about this model. Let me tell you a tiny bit more. Well, in particular, there are Vizon excitations, but they don't live on hexagons. They live on these 12-fold loops you can see here with actually 12 atoms running around. And at low energies, at low temperatures, it costs energy to flip a Vizon. And so W equals +1 is the low energy configuration. And if you do a numerical treatment of this system, you find that there's in fact a phase transition at finite temperatures into a ground state where the Vizons are absent. And here you see the results of Eschmann et al. In Trebst's group. And here you see, interestingly enough, the specific heat has 2 features. A high temperature feature where you start to form the quasiparticles, and a low temperature feature where you have a real phase transition, an Ising phase transition, into a state where the plaquettes have no flux running through them, W to 1. In field theory, this is known as the transition from an area preserving phase to a perimeter phase. This is how Wilson described it. There's one thing that's very peculiar about this. This is a phase transition without any order parameter, an Ising phase transition without any order parameter. Perhaps there's a non-local order parameter, but nothing local. Okay. So now we're going to take this model and we're going to look at the excitations in it, and we can then set the bonds to 1, and this is then the Hamiltonian that emerges. And now, when we diagonalize this Hamiltonian, lo and behold, it has a Fermi surface. Majorana fermions, when we Fourier transform them, are conventional fermions living in half the Hilbert space. And so if you do this diagonalization, you find there are 2 Fermi surfaces, but they're actually mirror images of one another. And so this is then the one unique Fermi surface that is there. And we then have a spin liquid with a Fermi surface in 3 dimensions that's exactly solvable. And it's worth taking a pause just at this moment. This would have been a dream Hamiltonian in the advent of the RVB theory of cuprate superconductivity. It's a solid example, completely solvable, of a spin liquid with a Fermi surface. But curiously, it's not an SU2 gauge theory or an SU or U1 gauge theory. It's a Z2 gauge theory. So let's take this model and look at what its properties are when we start coupling it up to electrons. We don't know how to dope it, but what we can do is we can condo couple it to electrons running on the same lattice. Okay, so that's what we're going to do. Here is the condo coupling. And the condo coupling, now we have to replace the spin here by a bilinear of Majorana fermions. That's where the fun begins. This was the decoupling that we discovered in the 90s, but didn't know how to control. Now we know the spin decouples as a Majorana fermion. And when we decouple this interaction here, what we find is it decouples in terms of a spinor degree of freedom, a charged spinor degree of freedom. And this is that charge E, spinor half spinor. This decoupling allows us to do a Hubbard-Stratonovich decoupling in which this spinor can now condense. And as a saddle point, what happens is the spinor acquires an expectation value. We have order fractalization. Moreover, in a particular gauge where the Z2 degrees of freedom have a fixed value, we have long-range order of this charge E object. Okay, so it's an example of something we call order fractalization. And so this then is the mean field theory that we have to solve. Okay. Okay. And the important thing about this model is that because the electrons and the Majorana fermions have completely matching Fermi surfaces, there is a susceptibility for charge E condensation, which contains a log. It's really rather similar to a BCS log. And this log will diverge at low temperatures. No matter how weak the coupling is, this will then lead to an instability. It is not a Cooper instability. It is a charge E spinor half condensation process. Okay. And when that happens, something interesting happens because the two Fermi surfaces together and one gets left behind. The conduction electrons are equivalent to 4 Majorana fermions, whereas the spins are equivalent to 3. And when you hybridize them, 3 of them say, oh, this is just like a Kondo insulator. And one gets left behind, and it doesn't know whether it's an electron or a hole, a spin up or a spin down, because all of its quantum numbers, its charge quantum numbers, have gone into the order parameter. Now, we can only solve this at weak coupling. And this is a very interesting model. One more thing. What is the nature of the order? Well, electrons Andreev reflect off this order parameter. And because they can hybridize with the conduction electrons, hybridize with the Majorana fermions, what can then happen is that you get Andreev reflection. When an electron goes into the spin liquid, it comes out not knowing whether it's a particle or a hole, and that leads to Andreev reflection. What you then end up with is a self-energy that you can calculate. This self-energy contains triplet components. It is also odd frequency, and it kind of avoids all the standard features of BCS superconductivity because it now has this feature that it's odd frequency triplet paired. And one of the other interesting things about it is that because the Majorana Fermi surfaces tend to be displaced from the conduction Fermi surfaces, the mismatch between the two tends to force the formation of a paired density wave. Okay, and so that's the summary of this model. And we don't know what the phase diagram is at larger J, but we can kind of speculate by doing a large J expansion. And at large J, what happens is that a conventional Fermi liquid forms, and the orbital degrees of freedom once again decouple, but now as just a pure orbital Kitaev spin liquid. And so we believe that this triplet superconductor will have a phase diagram that looks something like this. On the left-hand side, we have a kind of transition from what might be called a Majorana FL star into the triplet superconductor. But on the right-hand side, we should presumably have a transition from a Fermi liquid into a triplet superconductor. So when theorists have fun and play their games like this, they, of course, get very excited and they wonder, well, could it really occur in reality? Okay. And this is one of the things that physicists, theoretical physicists do throughout their lives. They revel in this weird possibility that occasionally the mathematics comes alive in reality. And we don't know whether that will ever happen for this model, but just to wrap up, there are ways in which it could actually stimulate our discussion of these strange metals and insulators. And I'll just, I guess I really ought to be ending. Let me give it a few more seconds just to talk about this. There is this great debate in samarium hexaboride between the conventional and the conservative. And so let's suppose we have some kind of neutral Fermi surface. And we can ask, well, what is then the nature of the coupling between the neutral fermions and the electromagnetic field? And various groups have thought about this. One idea is that you could get very large loops of ring exchange that couple to the enclosed flux. But whatever happens, whatever model you have, if they're to produce de Haaspen-Alfvén oscillations, then they must produce a magnetization. And that magnetization, of course, has to produce currents at the edge of the sample. Okay. And so if there's a neutral Fermi surface in samarium hexaboride, a phenomenological resolution of the conundrum would suggest a novel fluid that allows divergence-free circulating currents, but with an insulating longitudinal conductivity. What the hell does that mean? Well, if we look at the conductivity of a system that's isotropic, it contains two parts: a longitudinal part, in which the currents are parallel to the Q vector, and a transverse part, in which the currents have no divergence. Normally, at long distances, to avoid any singularities, these two conductivities come together into a single conductivity, and the weird term that goes like Q hat A, Q hat B disappears. But if we think about samarium hexaboride, it suggests that whilst the longitudinal conductivity is gapped out with a gap of about 3 milli-electron volts, if any of this crazy transverse, any of this crazy neutral Fermi surface stuff is true, we don't know whether it is, then we should have a conductivity of the transverse part that looks metallic, that looks Drude-like. And so this then suggests a crazy experiment. It suggests that take this system and look at its conductivity at much lower frequencies than have been observed. By the way, the gap of 2 or 3 millivolts is for the electrons. Twice that is 1 terahertz. And look at the optical conductivity. There's no sign of any gap in it, okay? And so could it be that we've already seen the gapless transverse excitations, and that if we go to lower frequencies, we'll see the fact that there is a DC limit to the transverse conductivity? This could be done using a pickup coil and would presumably have to be done in a magnetic field, okay? So that's a suggestion for the future. Let me just wrap up and further issues. So I've mentioned this transverse metal hypothesis, and one of the issues here comes from the fact that we have a broken symmetry solution in which the order parameter doesn't have stable vortices. And so one of the suggestions here is that when you have an order parameter that doesn't live on a cylinder, but lives on a surface such as a sphere, then the resulting fluid cannot carry a longitudinal persistent current, but will still support a transverse current, and therefore will be not a superconductor, not a metal, and not an insulator. It'll be something in between, and we call it a transverse metal, okay? Last and not least, you can play with these solutions we've got, and you can look for topological solutions. And we know they don't exist in 3 dimensions, but we've tried to look for them in 2 dimensions, and recently made some progress. It turns out that on the honeycomb lattice, this model actually produces a chiral topological superconductor. And the way we do this is we take the same Yao Li model on the honeycomb lattice, and we put nearest neighbor Kondo couplings in, and we find that there are solutions where the hybridization associated with both couplings switches on, and when that happens, we get a chiral edge state, Majorana fermions that travel in one direction on each surface. The red and the blue here are for opposite surfaces. And so this is the phase diagram we found, and so it does look encouraging. There are solutions of this kind that are topological. And that's the end of my talk. Thank you.